Given a polynomial p of x with degree 25, prove the following. So the first thing to note is that p of x is a polynomial which is structured like this: coefficient x to the 25th all the way on down until, I guess then I should include the addition sign, plus every other term all the way on down a to the 0, a sub 0. And we would like to prove that if p of r is equal to 0, then p of x must be evenly divisible by x minus r. And so first thing we're told is that r is a root. Okay, we know r is a root. And that's important, and what we want to show is that p of x is evenly divisible by this term, x minus r. So what we'd like to show, remember, something is evenly divisible, so p of x is evenly divisible by x minus r if I can multiply it by something else and not have to add some remainder. We'll call that remainder s. Now the first question is, what is this missing piece here? What would I have to multiply x minus r by to get p of x back? Or in other words, if I divided p of x by x minus r, what would I get in general? And what would I get? Well, I would get a 24th degree polynomial, so I'll just call it p1 of x. We've seen this notation before. And this would just be some 24th degree polynomial. But it doesn't really matter, because the way that we're going to prove it is we're going to then plug in r, our root. When we plug in r, well, we know that that is equivalent to 0 because p of r is 0. That was the first thing we were told. And when we plug this in, we're going to have r minus r times p1 of r, we've plugged that in, plus some value s. Well, what do we get? This is 0. 0 times anything is 0. So I have 0 plus s is equivalent to 0. Therefore, we've shown that s must be 0. And so the remainder has to be 0. Therefore, I could say thus, p of x is evenly divisible by x minus r. And another way of saying that, and this is an important piece, is this means that if r is a root, then x minus r is a factor, right? It is a factor, it goes in evenly to our polynomial. Alright, the next thing we're going to show is, well, we want to ask ourselves first, what is the maximum number of distinct roots that p of x can have? And our thought should be that it can't be more than 25, because that would mean that we'd have to have more than 25 factors, and it doesn't seem to make sense that if I had more than 25 factors, I could have a 25th degree polynomial. So we're going to say 25, and then we want to prove that it can have at most that many roots. How will we prove that it can have at most 25? We're going to assume that p has 26 roots. And we're going to list them out. It's going to be r1 up through r sub 26. And what we want to do is we'd like to show that from this comes some sort of issue, some contradiction that will prove that my assumption must be incorrect, that I can't have 26. So we're going to think about what could we do if we know all these roots. Think back to what we just showed. We showed that if you have a root, then you know a factor. So if we can factor out p all the way up until that last factor that should happen, hopefully we'll run into an issue. So by what we just showed, p of x is equal to x minus r1 times some other polynomial, we'll call it p1 of x, and there's no remainder because x minus r1 must be a factor. We just showed that it's evenly divisible. And so now we think about what will happen if we plug in the next root. And what's going to happen to my function? So if I plug in r sub 2, well, now I have r sub 2 minus r sub 1 times p sub 1 of r sub 2. And notice that this has to equal 0 because r sub 2 is a root. But this right here cannot equal 0. This cannot equal 0. So we must have that p sub 1 of r sub 2 is equivalent to 0. What does that mean? Think about that. That means that r sub 2 is not just a root of p, but it is also a root of p sub 1, which means that if r sub 2 is a root, what's a factor of p sub 1? Well, x minus r sub 2. So once again, I'm saying so a lot, but you can use some different words here. So p sub 1 of x can be written as x minus r sub 2 times some other polynomial, we'll call it p sub 2 of x. And it's important to note here that what's the degree of this polynomial? Well, think back all the way to the beginning. This is 25, it's degree 25. So p sub 1 must be degree 24. So this is degree 24, and so this must be degree 23 because we're multiplying it by a degree 1 polynomial, so on and so forth, right? And so we can use this, we can take what we now have for p sub 1 and we can plug it back into our original function. So I'll use a different word. Thus, p of x is equivalent to, and I have my first factor, x minus r1, and then just the next factor, right? I have x minus r2 times p sub 2 of x. Alright, now I'm going to go all the way down the road. I'm going to fast forward a little bit. I suggest that you at least do the next step, but then fast forward. And we'll get to the point where we have p of x is equivalent to, and we have all the factors, x minus r1, all the way up till we have x minus r sub 25, and times some other polynomial, we'll call it p sub 25 of x. Well, what do we know? We know that there are 25 factors so far, which means that all these factors together have degree 25. And guess what else has degree 25? Our polynomial. So what must the degree of p sub 25 be? No question here, it must be 0. So that means that this polynomial right here, well, it's got a degree 0, meaning it's just some coefficients, whatever the coefficient is, a sub d, because we have x to the 0th power, which is just 1. So what will happen when we plug in the next root? Well, if I plug in r sub 26, now I'm going to have r sub 26 minus r sub 1 times blah blah blah, all of these different factors with r sub 26 plugged in, times this coefficient here, and this is supposed to equal 0, right? Well, if things that are multiplied equal 0, one of them, at least one of them, must equal 0. So we think about, can this equal 0? No. Can this equal 0? No. Can any of the factors equal 0? It's impossible because these are distinct. Remember, we're saying that these are different numbers. So the only thing that could equal 0 is a sub d. So we must have, or another way of saying is, this gives that a sub d is equal to 0. Well, can a sub d be equal to 0? Look back at our polynomial p sub x. If a sub d were equal to 0, well, what would the degree of our total polynomial be? If a sub d were 0, our whole thing would be 0. So our degree would be 0. But this would force p of x to have degree 0. This is a contradiction, right? What does it contradict? It contradicts the fact that what's the degree of p of x? The degree of p of x is 25. But p is degree 25. So the most number of roots it can have, so it can have at most, I'm running out of space here, it can have at most, I'll finish it up here, at most 25 distinct roots.